class. So this is chapter 6 lecture in the book by Matthew Stevens, non-destructive testing and evaluation. So the first method that we were going to see of the non-destructive tests is the method in which eddy currents are used. So eddy currents, if you have studied electromagnetism, basically they are the induction current. It's an electric current that is induced. So it's an induced directional flow of electrons in the test object under the influence of an electromagnetic field. It actually follows from Faraday's law of induction, basically, that says if you have a time-changing magnetic field, you will generate an electric current. So of course, it's one of the four fundamental laws of electrical engineering that are called Maxwell's equations. Maxwell's equations, there are four. Basically, two laws are Gauss's laws. Basically, the first two laws, they basically describe how does a magnetic field and electric field exist. So one of them says that the magnetic field basically exists in closed loops. Basically, if you cut a magnet, you always have a north and south. You never can separate a north from a south. Gauss's second law basically says that the electric field has a source and a sink, either one of them or both. So then you have Faraday's law, which basically describes induction. Then there's Ampere's law. So these are the four laws of electrical engineering. And so eddy currents, basically, they're induction currents that come from a time-changing or a space-changing magnetic field. Any measured impedance in the flow points to the presence of flaws or other non-conformities. So basically, eddy currents, basically, they are useful. Sometimes they are actually unuseful. Like, for example, in transformers, for instance, you will see they laminate the cores. If you look at a core of a transformer, you'll see that's actually sliced. It exists in slices, and there's an insulation between the slices, and the main reason for that is to reduce the eddy currents. So again, eddy currents, they exist whenever there is a sinusoidal magnetic field, or a time changing, of course, or space, in other words, something that moves, a magnetic field that moves. So any measured impedance in the flow points to the presence of flaws or other non-conformities. So typically these tests, or actually these measurements, they are done on circular objects. Circular because it's easier, but the theory can be applied to any shape, basically. So originally, part geometry interfered, but highly sophisticated excitation sources and probes have broadened this application, so it can be used basically to detect any flaws, like, for example, a scratch or a crack in the surface. By the way, there's something that is very important. It's basically the skin depth. I don't know if you've heard of that, but again, remember, eddy currents, they exist with an alternating magnetic field. So in other words, you have an AC signal. So one thing is that for AC signals, the AC currents, they tend to distribute themselves on the outer surface, the outer shell of the conductor. So and as the frequency increases, the skin depth becomes lower, actually. So that's why, for example, the antennas, if you look at antennas, you will see the antenna is actually hollow from the inside. The reason why, because there's no need to make a solid bar, basically, because the current distributes on the outer surface. So the higher the frequency is, you actually don't need complete metal bars, conductors, but you only need hollow conductors. So to make it basically cheaper and lower in weight, conductors that are used for high frequencies are actually hollow. The eddy currents are the same thing. So eddy currents, they distribute on the outer surface. So that's why it's really good. It's a good method to be employed to detect scratches or cracks on the outer surface of the material. Evaluation of a flaw includes flaw size, of course, orientation, characteristics, and origin. You can get many information about the flaws and the cracks that exist on the surfaces. Let's look at this application here, by the way. So this is this will show. This is a video that shows how eddy currents exist, okay, and some applications of them. So let's look at it.
It is 9:48. It is time now to imagine it with the chief scientist from the Imagination Station, Carl Nelson. He has the electrodes hooked up like Frankenstein's monster. How you doing there? You all right?
Yeah. These are just two really, really strong magnets.
Wow.
And they're actually connected right through my hand. I've got a piece of copper here. Now, copper is not magnetic.
Okay.
That's going to be important for what we're going to do. Magnet will not stick to copper. So I'm going to put this very strong magnet away over here. And what I have here is a little pendulum, okay? So, Tony, I'm going to have you you're going to swing this thing back and forth.
Okay.
But we want to do it really, really close to the copper plate because a really interesting physics effect happens when a strong magnet moves close to a conductor. Now remember, this is not magnetic.
Right.
So go ahead and pull that back.
Okay.
And then it's about 6 inches. Oh, maybe right
Too
here.
far.
Too far. Right there. Let it go. Okay, hit a little bit. Let me pull it up a little bit higher.
Do you see that?
Do that same thing again.
How's the elevator business? It has its ups
So you
and
see an
downs.
electromagnet was generated inside the copper,
When it comes near the copper
and
plate,
it sticks to
it
the magnet.
comes to a near dead halt.
Huh.
It's like it's moving through molasses.
Wow.
So really
You see that?
complicated effect is happening here. The magnetic field is changing. It's creating circular currents in the copper plate. Those circular currents create a magnetic field that opposes the magnet. Sounds like a lot, but
Right.
the effect is it comes to a dead halt.
And it's all
very quickly.
created just by this one magnet.
Yes, and if you come near a iron bolt, it'll stick. But the copper is not.
Okay.
So we don't have to move just the magnet. We could move the conductor.
All right.
Okay. Now I want to show you this little apparatus I built here is a little dangerous because
Is this your erector set?
it is. It's kind of like a little. Can you hold this up here for me?
Okay.
Just stick your finger there and hold it. I'm going to show you what happens if we make a mistake.
Oh no, it's a guillotine.
Let it fall.
They're gonna have to take a look here. This is a carrot, a dangling carrot.
Carrot. Okay. We don't want to have that happen. Okay. So don't put your fingers down there.
Got it.
Okay. But no, we can use this effect. It's called eddy currents. We can use that effect. I've got 4 strong magnets here. Just going to lower those down to where the plate is. Do the same thing. Hold that up there again, Tony. For
All
me,
right.
if you could.
Yeah, I'll stick to this part.
I'm gonna go ahead and just let it go.
What, with your hand there? Oh.
All right. So check that out. When it stick your
What happens? You see?
No.
Ooh, come on, you'll be fine. So, is that not crazy? So
That is the trust test.
that's the trust test. Now, like I said, what's happening? Circular currents are flowing in this copper plate. If we damage the plate by putting some slits in.
So as you see, I mean, basically eddy currents are generated from a moving magnetic field. Of course, the magnetic field can be changing in time. There's time changing, or it can be changing in space. Okay, in other words, it's moving. It's not like a magnet that is moving. Okay, of course. So any of these two methods will generate eddy currents. Now, eddy currents, of course, they're currents. And another thing that is, if you notice in the video, that's very important. So they're generated on a metallic surface, okay, a conductor. It does not have to be ferromagnetic. Okay, it doesn't have to be a ferrous metal. It doesn't have to be steel. It doesn't have to be a ferrous metal, basically. But it has to be, of course, a conductor, like copper or brass or anything that conducts electricity. So, and another thing that you should see is that eddy currents, basically, because they are electric currents, they also generate magnetic fields. Okay, this is called the induced magnetic field. So, if you have a magnetic field that is moving, it will induce an electric current. The current will generate an induced magnetic field, which will interact with the original magnetic field. That's why you saw in the video the pendulum actually stopped when it passes over the copper. And the same thing when he dropped the copper, it slowed down when it passed by the magnet. So this is the eddy current effect. It has a lot of applications, but it also in some applications it is actually not wanted and is basically it's avoided. So This technique provides for a fast and effective testing of critical parts operating in a hazardous and harsh environment without contact with a test object. Of course, it's non-contact. It's non-destructive, obviously, and of course, it gives good indication of the faults on the surface of the conductor. So again, it has to be applied on to conductors, okay, electrical conductors, but not necessarily ferrous materials. It can be applied to any conductor. The second method that we will see is radiology. So this technique uses penetrating radiation to obtain an internal latent image of an object. The most common type of radiation are X-rays and gamma rays. So X-rays and gamma rays, they have very short wavelengths. Yeah, very short wavelengths enable them to penetrate substances that reflect or absorb visible light. Like, for example, wood, for instance, plastic, human flesh, for example. These can penetrate easily through these materials, X-rays and gamma rays. And of course, they are actually dangerous, of course. Precaution must be taken when if you run any source that emits X-rays. Gamma rays, it's not. I mean, it's not actually. You need to have to be trained actually, even just to get close to it. So they have very short wavelengths. Again, just like visible light, X-rays and gamma rays, they can expose a film and produce a latent image. So in other words, for example, visible light can penetrate through glass, and you can take an image of whatever the object is inside the glass or behind the glass, right? The same thing here. So X-rays, they can penetrate, for example, plastic, and they can see whatever is behind the plastic sheet or the plastic obstacle. For gamma rays, so X-rays actually they can penetrate through most objects. It depends on basically the density of the object. But typically, X-rays cannot penetrate through metals, so it will reflect actually from a metal surface. However, you can, if you increase the energy, it can actually see through some metals depending on the density and also depending on the thickness of the metal for the X-ray. So it depends on actually the energy. But typically, let's say it will reflect from a metal surface. Gamma rays, on the other hand, actually can penetrate through metals. It can penetrate through actually most metals, really, really thick metals. And that's why it's actually dangerous. The gamma rays actually, they both are very dangerous actually. So that's why precaution must be taken when handling any equipment that emits X-rays and gamma rays. So they can penetrate through visible, in the same way. So in the same way as visible light can penetrate through objects and take latent images through them, just like visible light can penetrate through glass to make images through it. X-rays and gamma rays are electromagnetic waves. Okay, so again, so everything that we have seen here, so gamma rays, X-rays, visible light, UV, infrared, radio, FM, microwaves, all of these are electromagnetic. They belong to the electromagnetic spectrum, basically. They're electromagnetic waves. So unlike sound waves are pressure waves. Okay, sound and ultrasound waves, these are pressure waves. They're totally different from light, X-ray and gamma ray and the electromagnetic waves. So let's look at, before actually we look at the electromagnetic spectrum, let's talk about wavelengths. So it's, you must have heard the word wavelength a lot. It's very important actually. Now a wavelength is equal to the speed of the waves divided by the frequency. So now what is the speed of propagation for gamma rays, for example? So the speed of the gamma rays or the X-rays or the visible light or radio FM or microwaves, they all have the same speed, which is the speed of light. Okay, now the speed of light, you must have heard that before, and you must actually memorize it. It's basically 300,000 kilometers per second. Okay, so that's equal to 3 times 10 to the power 8 meters per second, which is also equal to 187,000 miles per second. Now, acoustic waves, sound, ultrasound waves, basically, they depend on the medium. Okay, sound waves depend on the medium. So in air and the temperature, of course, medium and the temperature. So in air at 25 degrees C, they travel at 343 meters per second. Okay, meters per second. So it's a lot slower than the light, the speed of light. Okay, there's no comparison. Okay, so another thing that is important is that light can travel through vacuum. Okay, that's why we receive the sun light, every day. And on the other hand, pressure waves, that is sound, cannot travel through vacuum. Okay, it needs a medium. If there's no air, it cannot travel. So let's take an example. Question 1. A cellular carrier uses a frequency of 1.9 gigahertz. Okay, 1.9 gigahertz for cellular communications. What is the wavelength of the electromagnetic signals at this frequency? So again, so the wavelength, lambda, is equal to the speed of light, c, divided by the frequency. Okay, the speed of light, you should memorize it. It's 3 times 10 to the power 8 meters per second, divided by the frequency, which is 1.9 gigahertz. Gigahertz is billion, basically. Giga is a billion hertz. So 1.9 times 10 to the power 9. And so if you do the division, you will get 0.158 meters, which is 15.8 centimeters. Now, that's why basically, the objects, like a cell phone, if you actually take a measurement of the cell phone, always the dimensions of the object, basically that's the dimension of the antenna. Okay, the antenna is actually going to take, the span, the length of the object. So the dimensions of the object correspond to the wavelength. Okay, so if you have so for example, this wave 15.8 centimeters, it actually corresponds to something like that. Okay? So if you see, for example, a military vehicle that has, for instance, I don't know if I've seen them, the military vehicles with long antennas, like 2-meter long antennas, you can tell right away that basically the communication, you can tell the frequency right away. Basically, it's going to be the wavelength is the length of the antenna. So, for example, 2 or 3 meters corresponds to about 300 megahertz. Okay, so the same thing. Like for example, a cell phone, 15 centimeters corresponds to 1.9 gigahertz, and so on. So you can tell basically the frequency that is being used for communication by looking at the size of the antenna. Okay, because it has to correspond to the wavelength. So let's take another example. So question number 2. The red light lasers at a wavelength of 700 nanometers are commonly used in spectroscopic applications. Like, for example, if you want to use, for instance, something called Raman spectroscopy, they will tell you which wavelength do you want the laser. So typically, for most applications, you will need something around 700 nanometers. So it's a very commonly used application. What is the frequency of the red color light at that wavelength? So again, we have here lambda is equal to c divided by c is the speed of light divided by the frequency. And we have lambda is given 700 times 10 to the power negative 9, 700 nanometers, is equal to 3 times 10 to the power 8 divided by the frequency. And you will find that the frequency is equal to 4.28 times 10 to the 14 hertz. Okay, so it's gonna be basically in the it's gonna be a few hundreds of terahertz. Okay, 428 terahertz. Okay, so this is the wavelength. It's very important to know the relationship between wavelength and frequency. and to know the speeds, the speed of light and the speed of sound in air, okay, at 25 degrees. So let's look at the electromagnetic spectrum. So here, as you see, I'm sure you have seen this before. It will show you basically the range of different waves and their wavelengths, okay. So as you see here, the visible light, which you can see, is only this small strip of the electromagnetic spectrum. This is the only part that you can see, okay. So it extends from slightly below 400 nanometers to about 800 nanometers, okay. As you see, the red color is here basically in the 600, 700 nanometers. This is the red light. It has the longest wavelengths of the visible spectrum, okay. The shortest wavelengths are the violet. On the other end, the shortest wavelengths are the violet. The violet color has the highest energy, okay. The violet waves have the highest energy, and the lowest energy is in the red light. So for example, if you look at other ranges, like for example, of course, below the red is going to be infrared, okay, the infrared. Then you have here above, of course, the violet, we're going to have the ultraviolet. Then above the ultraviolet, they're going to have the X-rays. Then the highest in energy is going to be the gamma rays. So the gamma rays, they have the highest energy and the shortest wavelengths, okay, the shortest wavelengths. On the other end over here, you have radio, the radio waves, basically FM and AM, for example, and so on. So these basically have the lowest energy, the longest wavelengths, okay, the longest wavelengths. So microwave also is somewhere here. So and the radar. So these are basically this is the electromagnetic spectrum. These are here some applications, basically of different frequency ranges. Notice here again. So as the frequency increases, the frequency increases, of course, going towards the gamma rays. The wavelength becomes a lot shorter. Okay, look here how it has a very short wavelengths, and here very long wavelengths. Okay, it's very important to understand the electromagnetic spectrum. Let's take an example here. So if we have, for example, 4 waves, we have a sound wave. Again, a sound wave is a pressure wave. Okay, a visible light. We saw how it actually extends between about slightly below 400 to about 800 nanometers. Okay, X-rays. The X-rays are going to be very short wavelengths, and the gamma rays, which are the shortest of them all. Okay, the shortest of them all in wavelengths, but the highest in energy. Now the sound waves, they can penetrate through glass, but they cannot penetrate through vacuum. Okay, why? Because a sound wave is a pressure wave. It needs a medium to propagate. Okay, no medium, they cannot propagate simply. All right, there's no pressure. So vacuum, it cannot propagate through vacuum, so it will stop over there. Visible light can, of course, travel through vacuum. That's how the sun actually, emits light to the earth. So it can emit through vacuum. It can penetrate through glass, but wood is opaque to visible light, so it cannot penetrate it. X-rays, on the other hand, they can penetrate through glass and wood, and they will reflect from steel. Actually, like I said, X-rays you can actually depending on the density of the metal, but it can actually penetrate through the metal if you increase the energy. But of course, not not for a large depth. Gamma rays, they have the highest energy, the shortest wavelengths, and they can penetrate through metals. In fact, gamma rays actually can penetrate through really thick steel. I can't remember what is the thickness, but actually it can penetrate through a thick block of steel. So radiology, of course, we're still in radiology. So X-rays are emitted when an electron beam strikes a solid object. This is how they basically generate the X-rays. Basically, this is one of the methods. Natural sources of gamma rays are disintegrating radioactive substances such as radium. So these are basically radioactive substances. Radium is commonly used. Of course, like for example, uranium. Uranium isotopes also emit gamma rays. So this approach can point to lack of homogeneity of the chemical composition, non-uniform density, internal cracks, voids, and discontinuity. So basically, when you use radiology, you can find, like for example, here, look at it here. For instance, this is an X-ray image of a SIM card. You know the SIM cards in the phone. I don't know if you recognize the shape here. You see the shape of the SIM card. You see this corner here. Look at it carefully here. This is basically the electrical circuits inside. So you can actually see, inside the SIM card how the electrical circuit is, for example, using X-rays. So it can tell you, for example, there's a discontinuity, or for example, a cut wire, or a crack or anything. So radiography can be used for the evaluation of forgings, of course, welds, very commonly used application. Casting is non-metallic fabricated parts. So tomography. Tomography basically, like for instance, a CT scan, a CT scan unit, for example, in a hospital. So these basically, tomography basically, in this approach, hundreds of images are taken from different angles. Okay, so it takes hundreds of images, and then it constructs the 3D model. Just like, for example, imagine that you want, for instance, I'm sure there's actually software, computer software, in which you can just take pictures, from different angles of a house, for instance, and it will construct for you the house, okay, based on these pictures. So the same thing here. So it takes hundreds of images. Of course, the software needs a lot of processing. The higher the number of pictures, the higher the processing time it needs and power. So CT scans provide a 3D image from a combination of X-ray scans at different angles. This method has been used to analyze assembly parts and detect cracks and defects. Let's look at this here. I think there's a video. So this is a CT scan of a webcam. Look at the circuits inside. Do you see these? The circuit parts. So it's a webcam. Now you can see the internals of the webcam using a CT scan. So tomography again, it stands for a technique in which hundreds of images are taken from multiple angles to construct a 3D model, a 3D image. Then there's a very similar approach, which is magnetic resonance imaging, MRI. MRI is actually, so it's another, it's an expensive, of course, method to use. The difference is that here, MRI actually doesn't use radioactive materials. Okay, it's based on magnets. Okay, so MRI is in fact a tomography imaging procedure that allows for the production of multi-dimensional images. It is capable of generating multi-dimensional images in any orientation without the ionization requirements or the need for the use of radioactive materials. So unlike the X-rays and gamma rays, it's actually safer, let's say. But still, it's actually a very expensive method. So now, let's say very common methods, very commonly used methods: liquid penetrant, and there's the magnetic particle method. So liquid penetrant here in this method is used for detecting surface cracks for metallic as well as non-metallic objects. So it's used on, of course, both metals and non-metals. And here, basically, what happens? Yes, can detect extremely small open surface defects. In this method, a liquid penetrant with a dye is sprayed on the surface and left to dwell, then cleaned off. A developer film is then applied and draws liquid from the cracks to the surface under the capillary effect. So what happens here? Basically, you spray. First, it has to be cleaned. Of course, the surface has to be cleaned really well. Then they spray a liquid with a dye that has a dye in it, and then what happens is that, well, of course, you clean the liquid, and the liquid will go inside the cracks, as you see here. It will go inside. If there's a crack, it will go inside the cracks, and then after that, you deposit a film. You spray basically a film. Actually, no, you don't spray it directly. Actually, but I mean, you basically apply it, and what happens is that you leave it for a few minutes, and the film will allow the liquid to come out. It will actually drag it, from inside the cracks, and it will come out, and then you will see clear spots where there are cracks. So it's used basically on solid surfaces. The surface does not have to be metallic or ferrous or non-metallic. It can be of any surface. So this is liquid penetrant testing. As you see, so you apply the liquid penetrant, it will go inside the crack, and then you apply the developer. The developer will allow the liquid penetrant to come out from the surface, from the crack. The last method that we're going to see is magnetic particle testing. So this method only applies to ferrous materials. Okay, only applies to ferrous materials, anything that can be magnetized. All right. And the reason for that, as you see here, is because you are going to have an electromagnet. There's an electromagnet. The electromagnet, when you turn it on, is going to generate a magnetic field. Now, the magnetic field has to run through the surface. Okay, so it's gonna use the surface to close the loop and come back. So the field lines will go from here through the surface and come back there. Okay, so if you have studied physics, the resistance to magnetic fields is called magnetic flux. It's called reluctance. Okay, so the reluctance actually, if you don't use a ferrous material like steel, what's going to happen? The reluctance is going to be extremely high, and it's not going to give you really any measurements. Okay, the measurements are going to be extremely weak. Okay, and but on the other hand, if you use a ferrous material like steel, the reluctance is going to be extremely low, and the magnetic field lines will be strong. Okay, it will be very strong magnetic field lines that will basically, they will allow the particles you're going to spray first iron fillings, of course. The iron fillings, they will line up with the magnetic field, okay, with the magnetic field lines. So force lines are formed around a magnetized steel bar. These lines can be applied by sprinkling fine iron fillings on a clean magnetized steel bar. A crack, inclusion or any discontinuity on the object will disturb these force lines. So if you see, when you spray when you actually sprinkle the iron fillings, if there's a crack anywhere, what's going to happen is that even if it's not visible, not only cracks, but also voids. If there's a void, like for example, on for example on welded parts. Okay, on welded parts, if there's a void inside, then it can, you can tell actually the location of the void because of the distribution of the iron fillings. Okay, so I think there's a picture here. So as you see here, if there's a crack, it's going to disturb the magnetic field lines, and you're going to see the fillings concentrating here. Okay, So it's a really good method. It can be used to detect voids or cracks. And it's very commonly used actually, but it has to be applied only on ferrous materials. Okay, it cannot apply on non-ferrous materials. So this brings us to the end of this lecture. I put questions for as a homework. Please do the homework and refer to this lecture to do the homework. Thank you and have a good day.